Hello guys, I'm Sergio and today I will show you how to run BAME to estimate the emissions in a European signal. First of all, you have to, some quick comments, it's not only for Europe, it can be used in Africa and in Latin America. The key thing is that they use the latest emission factors available until Euro 6 and more than ABCD. You know what I mean, okay? First of all, what you need to do is update your BAME estimation. Running this remote, install GitHub code atmos/BAME, okay? And then, and then we will, once you have BAME updated, you write this BAME : get project. The first argument is the Euro city. I mean, this could be like any city. This can be any city with Euro emission factors, right? I mean, this will be the new name for this new directory, okay? But the this has to be EU_BU_CHEMI, okay? And now it's downloading the model. Specifically the project, okay? It weighs this size because it already includes a worth input need CDF file to make the calculations. And now, take attention of this, bear with me. We go to the yellow icon of the folder, we click this, and then we found our directory, any city with Euro EF. And then we need to open the file main.rproj, that one, open, confirm, and now we are going to have our new directory. Now we are in the project. You can check here right here, we see any city with Euro UF. This is the thing, the activity data comes from Manizales, but you have to, I will keep running the model, everything right now, just like that, okay? And I will explain you the details so that we're not going to waste time in doing the estimation. Some things before running the model. This is the header. Every time that you run the model, first you, for instance, you did one estimation, but you are not finished. Close your computer, close everything, and then when you open again, you click on this, and then you go and run it in the part that you finish, okay? There are several blocks. The first block, the block 0, is the configuration. Here you need the configuration, and all the configuration depends on this Excel file that I will explain you in detail in 1 minute. The block 1 is the network, this one, okay? Which includes this information that are related to the network in the geo package. Second one is the traffic. Here we have the information about the traffic, the categories, and so on. And also on the speed. The block 3 is the block that needs the information to do the proper estimation of the emissions. But before estimating the emissions, the first part will be estimating the fuel consumption, so that the fuel consumption activity is calibrated to match the fuel sales on your area of study, okay? After that, then we go in the estimation of the exhaust emissions using these parameters, and then we go and estimate the emissions as here using this script. After we estimate the hot exhaust, then we're going to estimate the cold start emissions. After that, we estimate the evaporative emissions, and after that, we estimate the resuspension emissions for paved roads. Here are the seed parameters that you can change as well. I haven't incorporated the wear emissions, but I will do it soon. And after that, we have the next block is the post estimation. I don't have the number, I think this one was third, but the fourth block is the block number 4 is the post estimation, okay? Here we have also the plots, which is the block 5, and then after that we have the chemical speciation, And finally, the WRFCHEMI. And put it like this, you can then easily navigate on the different parts, right? As you see here in this menu of RStudio, which is really convenient. That said, what I'm going to do is I'm going to select the whole code, okay, with Control A, and then I will, with my left hand, I will click on Control, and with my right hand, I will click on Enter. But before that, as I like colors, I will call the library color out to have a nice set of colors on the submission. And then now we're running. As it's already running, let me explain you a little bit about the first part, which is the configuration. As it's running, so we don't have any problem with that. We go into any city with European Emission Factors, and then we go into this part, which is the Excel file. Here, the Excel file, here has all the configuration that you need to estimate the emissions, all the information. There are some more sheets than needed, okay, but they help you to understand some things. The first sheet that you need to look at is the intro. Here we see the object is traffic. It consists in volume of traffic at the morning rush hour of the city of Manizales, a Colombian city. This information is actually this one, okay, Manizales city, because this is just you need to have this in order to improve you need to get your own data. The better your data, the better your estimation, just like that. Now, if you see the sheet metadata includes the definition of vehicular categories and properties according to the European Emission Guidelines. Let's have a look at this. So, the first column you will see is family. In family, when I see family, I'm talking about passenger cars, light commercial vehicles, trucks, bus, and motorcycles. But then the column vehicles has this nomenclature, this classification according to European Emission Guidelines. And you see here this number vehicles, the column vehicles is key, because it will be used across the whole van estimation. Then we have name, which is the extension, the explanation. Then you have the fuel, the size, trips per day. This is really important, which is how are we going to separate the fleet. This is for, here we indicate which survival function are we going to apply to take out the scrapped vehicles. These are the survival parameter A and B, and I will explain you a little bit later. Sulfur, this is name of according to the category of European Emission Guidelines as well. And this is the segment for the European Emission Guidelines, the mode, slope, load, average speed, the driving cycle that we are assuming that is driven. But it's not necessarily that is used that. This is more when you're doing a top-down estimation, but here we have the speed, actual speed, okay? But also this can also be used in the case that you only have the volume of traffic at the streets, but you don't have the speed. Then you can use these parameters to estimate the speed. Here is with different driving cycles for different buses, and then the average distance. Okay. And what else? And this is the name according to the older nomenclature, because there's two things. One thing is that up to 2016, the European Emission Guidelines has this nomenclature: passenger cars, 4-stroke, 2-stroke, and so on. Okay. But since 2007, which was before passenger cars with 1,400 cc or lower, this is just mini, and then small, and then medium. So that's it. The fleet age has the annual sales or registration of vehicles in them. Then we'll read the columns that I just mentioned: survival, survival param A, survival param B. 2, apply the survivor function and just work with the big fleet in circulation, okay? Taking out the scrapped fleet. And this source, if you take a look of this is used with the function age. The survival, the default values right now are according to the Brazilian fleet, but I have like 4 or 5 type of survival functions all applied to cars, and I'm seeking their literature. And also you can use your own as well. The temporal factors, which is here, if you see, okay, this is here, is the temporal factor to project the morning, the volume of morning rush hour to the different hours. And if you see here, it's consistent in the ratio between the fleet at different hours to the hours of the morning rush hour. In this case, at this hour. That's why if the original fleet, we divide the original traffic count at that hour divided by the traffic at that hour, returns in this value. In that way, we just multiply these matrices, and we have the extent projected traffic flow at these different hours. Then we have the mileage. Mileage is simple as the distance driven, but average distance driven by each vehicle by age of use. Here, the default values that I'm adding here are the two average from 2 million odometer readings in São Paulo, published as well. You can also, this is the idea is that you don't have to use this, you can use your own data, and that's the idea. Then we have the fuel. This is the chemical composition of the fuel. Okay, this is the chemical composition of the fuel. And the bank will read fuel density, consumption liters, year, month, and region. Let's take a look. Currently, this is data for Manizales, okay, as Colombian city. And it's in yellow because we are going to read this column fuel. This is the density to transform from volume to mass. This is the fuel consumption. And what we're going to do here is that these are the data what is needed, region, because you can have several regions, you just want to just select them, maybe you have different months. Here the basis that I'm working here is month because it's more consistent with several type of other emissions inventories such as Edgar, despite that we're using only emissions for 24 hours. We know that because their TPS covers 24 hours. But as I've done it before, you can use it as well for the TPS. You can use it for a whole month, like every hour of a month, and then you can use that. So you can. You're not restricted to 24 hours. You can use 1 week. You can use 1 month, whatever you want. And then the Euro standard. This is the Euro standard according to your European emission guidelines, as it is here. Okay. There are two things. If you see here, this is the nomenclature for 2019, and this is the nomenclature, the older nomenclature. Okay. Here, in order to maintain consistency between the different estimations, what I'm doing here is that I'm using only this one, and all the main functions will read Roman numbers, okay? Despite that they have the latest emission factors, the latest technology, and so on, here I'm using this because it's easy to maintain and harmonize the different emission factors, nomenclature, programming, etc. It's easier and it keeps consistency. Actually, I don't know why they went from Roman to Arabic, and I don't know, but the thing is that it works now with the latest technology, and that's fine for me. Okay. I think it's better. Anyways, they have their own reason. Then we have the check is the technology associated with vehicular category by age of use. And this is regarded for the emission factor for the 2019 guidelines, okay? This is only, I think it's only for Euro 3 that are required. And then you can have some options. You can check on the documentation of the package. Then we have the monthly temperature. Here Brain will read region, year, month, and temperature. This, for instance, here you can put a loop and estimate the emissions for the different, consider the emissions for the different months. And that's the idea. You can have several cities. The idea is to filter, make it easier. Then we have the fuel specification of the chemical composition of the fuel of your study area. And here we have which is needed. For gasoline, these parameters, and for diesel, these other parameters. These are the default values, and these are the units required. The idea is that this estimation will make that sometimes when we have fuel for better quality, like less sulfur or something like that, this will result in lower emissions just because of the quality is better. Okay. On the other hand, so this is the objective is to incorporate the decrease of the emissions based on the improved quality of the fuel. And then we have at the end, this part is optional. You can turn off or turn off or turn on or off on your R script. But this is a really cool thing. It's about the inspection and maintenance programs. Based on a review, based on equatorial data, and based on a review that I did into the US mobile and US moves emissions models, I studied how they manage the inspection and maintenance programs. Here I'm doing, I generated quite similar equations, but I think that my approach is a bit simpler, but it also can help you to evaluate the impact of the inspection and maintenance programs in your city. The first sheet is I am okay, like I am okay, and consists in the percentage of vehicles that approves inspection and maintenance program by age of use. For instance, this is based on Ecuadorian data, right? For the passenger cars, meaning with gasoline, at the year 2017, 77% of the cars approved the inspection and maintenance program. I don't know what is lower than the year 2016, which is 83%, but those are the numbers. I crunched the numbers and I calculate the average, okay? So once we understand that, once we understood that, now we can see the parameters for CO, hydrocarbons, NOx, and particulate matter 2.5, which are all the same equation. The average of the emissions ratio of the reproved and the approved. The ratio, reproved divided by the approved. That's the idea. So the ratio of the average value of the reproved, which is higher emissions, and the denominator is only which one are approved on that year, is 87. And that's the idea. Okay. And that's it. Now we have, I think that we must take a look at our estimation. And also here are the CO, hydrocarbons, NOx, particulate matter. This how this is work, and the idea is that you must change according to the data that you have. And now look at this. It's beautifully it's estimating the emissions right now of hot exhaust emissions. Really cool. Now I will explain you the output that we are seeing here, so that you understand the output that we are seeing here, and it's good because it's good understanding to understand, right? Sorry, yeah, but no. Okay, yes. There's block 0. I think I will change. I will start using natural numbers instead of this number, like starting from 1, like R. But the thing is that this part, we select the language that we're working in the path to the our Excel file that I just showed you. And then here we read the sheets, and here are the sheets that I show you. And the metadata, we're going to grab the matrices, mileage, TPS, I am okay, and so on. This is not even usable. It's there, okay? And yes, and here's the network that I show you, and then we'll project as it's projecting the traffic for the different hours, if you have the peak speed, the speed at the morning rush hour, and also we have the free flow speed at the morning rush hour, at the speed limit, I mean, then with applying the BPR equations, we can project the speed at the different hours. So now let's take a look of the speed. And also there are so many inputs that here by default we're plotting everything because we need to check that everything is okay. For instance, this is the fuel. So because you need to check that everything is running smoothly. Now the speed is here. Look at this. This is the projected map of the projected speed. For this, I will look at how this is a little bit darker than this. This is a little bit whiter in yellow because at the scale, more darker means higher speed, and more yellow or yellower means less speed, right? But now let's take a look of this other speed that I love it. Just simply, very simply, but it helps. This is the average speed for the whole street for the all hours. The average speed is around between 35.5, I guess, kilometers per hour. But if you check here, the lower speed is at the morning rush hour, and then the lower speed again is at the evening rush hour. These are the 24 hours, and this is the first street, the second street, and so on, so on. Because there are some streets that the higher yellower means slower speed, and darker means no. Here is the opposite. Darker means lower speed. Yellow means higher speed. So we see that there's some high speed. And this is the average again, but this is considering the average by street. This is by the average by hour, and this is the average by street. Nice, right? It took me a lot of time doing that thing. And if you take a look of let's take a look of the temporal factors for passenger cars. These are the temporal factors for passenger cars at the zero, at this point from 1 to 24 means that at 9 is represent between 0 or 8, between 8 and 9. In the considering the 0 to 23, I understand myself perfectly. And then we see the values, the two peaks. Everything, if you have better data, it will be better. But now take a look at the passenger cars. These are the passenger cars. Now take a look at the trucks, right? Different routes. This is very important because if you have different groups of trucks, it emits more NOx, right? And the passenger car emits more gasoline, more CO and hydrocarbons. It plays a role, especially temporally speaking, about the generation of the photochemical smoke. CO, especially considering the secondary pollutants like CO and particulate matter. The secondary particulate matter. I mean, all right. So that once that, then we have the traffic, okay? And the traffic, these are the inputs required. This is, you have to put it by default. And here we are using the speed because we are using emission factors that depends on the speed, okay? This is the details of trucks, traffic family. And this is the traffic family, is the composition. Look how there are more buses than trucks, which use diesel. But look at how many passenger cars, motorcycles are using gasoline. A few electric cars, and a few passenger cars with diesel, and that's more. And there are some hybrid. In this estimation, I think I'm not considering hybrid, but I have emission factors. So we generate another project, another video where you can simulate the impact of more or less hybrid vehicles. And then it generates different cool things. And also you need the capacity. Okay, you need to know the capacity of your data. In this case, if you're using emission factors that depend on speed, actually. And now there are some other cool things here. Maybe this one. This is based also on the Ecuadorian data. the equatorial data here says that there are lots, the most important vehicle in circulation, the most numerous, the high amount is for motorcycles using 4-stroke between 50 and 250 QBCC. This is the size of the engine. However, if you go to, I don't know, Warsaw or maybe other European city, you will see very few motorcycles. So this composition will change, and this is important. But then we have lots of passenger cars, buses, and then few light commercial vehicles in living less trucks, more from this category. Yeah, now we are plotting the emissions. This is cool. Now we can go to the estimations. And the estimation says this: we go grab the input data, okay? We use the input data. We use also the fuel that we estimated. And the first thing that we do, our estimation, is the first thing will consist in, as we enter the fuel sales of our area study, our model will estimate also fuel. But in order that our estimation is good, they must match mathematically, right? Mathematically. And here's the first, that's why the first part consists in only fuel evaluation. And the fuel evaluation, what we'll do? The fuel evaluation first estimates the fuel consumption. And then the first estimation says, the fuel sales are 2,461 tons of diesel, but our estimation results in 7,000, 2.8 times more. And the same with gasoline, for 2.25 times more. So then we use these values, the ratio of the estimation and fuel consumption and fuel sales, and apply to the activity data, estimate the emissions again, and now, yes, we have a nice estimation. This is the estimation, and this is the data, the fuel data for fuel sales, and now we have a consistent estimation. Because the idea is this: once we have the activity data calibrated, then we can estimate the emissions, and not before. This is for several reasons, but this is the most important, and I would say that this is the key category of the vein model. Thank you. Now we can estimate the emissions. Oh, this is crazy, it's going crazy. Oh yeah, I know we are getting a lot of output. Oh, I'm kind of slow. The estimation of here is the estimation of the exhaust emissions. Once we have the estimation of the exhaust emissions, we have we select, we are working, we can switch on and off, true or false, as you wish, okay? Obviously, if you click on true, you will have higher emissions. And then here in this part, we are generating we are selecting the emission, the pollutants that we are going to use. Just keep it this way, estimate the emissions, the hot exhaust emissions. Look at these beautiful outputs, colorful outputs. And then we are done. And I haven't even finished explaining this, and we are done. It's good. Here, estimate the cold star emissions. Then we estimate the evaporative emissions. I think that I won't be able to find them now because Wolfgang generates too much output. Okay. Then we estimate the paved roads. In the paved roads, there are some key parameters about our estimation, which also depends on the temporal factors. It also depends on the data that we are using. Okay, you're all grown up. You have to do better input, better estimation. Correct. But this is the seed. Here I'm suggesting to use the seed for Chile because in Latin America, there are a lot of the seed is really high. Especially if you're in a dry city. But if this seed change, you have to change. And also you have to correct your estimation if there's rainy period of time in your study area, in your study, as explained in the AP42 emission factors. Well, you can change these values as you wish. Here is the part of the paved roads. Then we have the post estimation where we are going to this is not 30, it's 45, but it doesn't change. This is only for is 30 in this case because we are using 1 month, the number of the days of the month. But this is very important, okay? All the estimation done by Bain, they has to consider UTM project coordinates, not lat long. If you're using lat long, we're using SF, which relies on S2, the geometry programming, the geometry package, the Google, used by Google, which is really good. But in this case, it's really slow, and the accuracy, we're not going to lose accuracy if we're working with UTM. So please only use UTM coordinates, and that's the idea of CRS. Okay. Other case it would take forever, and maybe you wouldn't even able to finish your run. Then we have the plots, some nice plots. Okay. Here again, here I have 25, but this is 0. But these are not going to change in any way your input, your outputs. Your outputs are temporarily, spatial temporally according to described correctly. Once we have that, then we can I add in a loop so that we can generate chemical mechanisms for CBMZ, ZB05, Saprak 99, but you can generate for all of this. Okay. Yeah, RACAM2 and so on. And once we have the same mechanisms, we can generate WRFCHEMI emission files for the same, right? For the same chemical mechanism, which was done here as explained you. And there are some things that also you need to consider this molecular mode, but let's stay with me on the WRFCHEMI. There are some things, the English, the language, this is the number of columns and rows as shown before when you're running running your read. Here for instance it says, you need to write that number because then we are going to use this. We are working with 24 hours, and then we can change the useful emissions. We can generate, or if you want the useful emissions 1 or 2, it depends on whatever you want. Here we're using just 24 hours, but it can also get generated for useful emissions 2 and hours. Okay. Sometimes we are doing an estimation of another city which is not our city and it's a different time zone. You can generate as I'm right now in Sao Paulo, and here now it's assuming that the estimation is in Sao Paulo, but look at this, it's assuming the estimation is in Sao Paulo for Sao Paulo. But what's the time difference for Manizales? I think it's 2 minutes 2, I don't remember. Okay, but here you can change 1 hour plus 1 hour, -3, and then in this way the WRFCHEMI file, the WRFCHEMI emissions file, we have the emissions at the time correct, because the emissions on the WRFCHEMI file must be an UTM. And this is only the only idea of this is to generate emissions for the UTM. Once this is done, I would like to take let's take a look at our WRFCHEMI. So here WRF CBC NS view. This is our early study, pretty small, but this is correct. But also you can change, we can check more. This is the diurnal cycle for Manizales, the tons, and this is ton per year, but actually it's ton per hour. What else? Age. These are the emissions by age of use. I love to call this type of plot a signature, as I publish in my papers. I think it's kind of unique, you know. I mean, you can generate the emissions with using MOBs and maybe other models, but generating the emissions by age of use is something like I never saw before. I'm really happy about that. Despite that doesn't look very good, but the good thing about this is it explain you where you have to put the management. If you want to put the emissions, here we have a problem because the older vehicles, as we know, older vehicles emit more, but also we have a problem here. This is really good. WRF these are the work emissions, the city that we saw. But right now, let's do it like this. Let's take a look at the street emissions of CO. These are the emissions at each street. Obviously, there are some few streets that has higher emissions. But if you look at the downtown, we have many emissions with lower values. Okay. Well, so how can we communicate this? But I was reviewing a paper nowadays, and I was discussing that because we need to communicate this in the best way possible. And here are the same emissions that I showed you before, the same mass. If you integrate the mass, is the same, but this is only as aggregated conservative mass, conservatively aggregated emissions and the grid sales by the WRF input file. And here we see a totally different pictures. More of the emissions are in this part, despite that they are like this cell, which high emissions, but not a big deal. Here, the key thing is that as we have many streets, despite they can have low emissions aggregated, integrated in a space, we will have this other picture. And this is the idea that you have to take care of many times. Any other cool thing to show you before finishing the video? Total particulate matter. Yeah, these are the total particulate matter. Most of the emissions are here by buses, but also by motorcycles. And you might say, why? Motorcycles are not the main emissions there, but the thing is that there's also paved roads. So that's why we have gasoline with too many particulate matter. I mean, gasoline emits particulate matter, but very few in comparison with diesel vehicles and trucks. But here are the two types. And as we can see here, right? But most of the emissions are from paved roads and less from exhaust emissions, and all exhaust only for very few, only for more for diesel, right? Look at the buses. And also, again, all these will vary, and you will have different values if you're working with a different configuration. But here, wrapping up, thank you for listening. Thank you for watching the video. Subscribe and all this stuff that people talk and whatever. Thank you. And this is my last Sunday on Brazil. I'm moving to USA. We work at NOAA. And yeah, thank you. And write me and keep in touch. And so whatever you have said, thank you. See you. And stop. And bye.